Good morning. We are going to go over our practice exam today. And this practice exam should be really, really helpful to you guys for studying for your final on Wednesday. So let's go ahead and get started with that. I'm just gonna be having to flip back and forth because I don't have a printed copy. So just bear with me today. I guess I could share the screen. Sorry. Let's see. Well, now I don't know where I went. Okay, there it is. All right, let's see if I can share the screen. Hmm. Oh, okay, I don't know what to do. Let's see. Okay, here we go. All right, so let's look at number 1, which was convert this number here into scientific notation. Let's see, I might just do it here in pages for you. All right, so what we're gonna do is first you want in scientific notation your decimal to be after the first digit that's not a 0. And it's always going to be after that first one there. So after the 1, it wouldn't be after any of these zeros because they are not significant digits. It's going to be after the first digit, and that means it's going to be right here after the 1. So you're going to have 1.500. And then you're just going to, so here I left everything after the decimal there and put it after the decimal. Then I'm just gonna go where I placed the decimal and count backwards to where I started. So here we were, and we're gonna go 1, 2, 3. So 1.500 times 10 to the negative 3 because we went backwards. I can't tell if anyone's joining. Let's see. Okay, no one's here yet. All right, I'm just gonna keep going. Okay, number 2. How many significant figures does the number have? Okay, so anything that's a 0 before a digit is not going to count as significant. So this 0, this 0, this 0, not significant. Anything after that and that's after a decimal, even if it is a 0, is going to be significant. So 1, 2, 3, 4, 5. Your answer would be C, 5. Because again, these zeros don't count because we haven't had an actual number yet. Once we get to the 3, that's our first significant figure. And then, of course, the 2 and the 9 will be significant. And these 2 zeros are also significant because they're after a decimal and they're after digits. Okay, so C5. All right, the next one. How can you determine from the periodic table whether a compound is ionic or covalent? Here, I'm going to put the answer here. Okay. Let's see. So as we learned a lot of modules back actually, ionic means a metal and a non-metal. Covalent means all non-metals. So if you're looking at your periodic table, you remember the jagged line that I showed you? Let me see. I'll get mine out. I'm gonna have an extra one here. Actually. Okay, I'm just going to show you the one in the book because that's the one I have the closest. All right, so here we have our jagged line on the periodic table that's bold, and everything that's pink here and then hydrogen, those are all non-metals. Everything else is going to be a metal, the green, the yellow. So if you look at the periodic table and it's involving only the pinkish red ones, red, whatever color that is, those are going to be covalent. If it has a green or a yellow and a red, then it's going to be ionic. And you can word that however you want. So let's see. I'm just going to put what they put in the answer key. If a compound has a metal in it, it must be ionic. If it has no metals, it is covalent. That just tells us what ionic and covalent are, so now we need to say how to figure that out by looking at the table. Atoms on the left of the jagged line on the table are metals, and atoms to the right are nonmetals. Sorry, I spelled that wrong. Okay, let me take that up. There we go. All right, that's your answer for number 3. Number 4, for the following compounds, if the name is given, write its formula. If the formula is given, write its name. All right, let's start with letter A. And let me find where I'm at. Okay, so they give us diphosphorus pentaoxides. That means I need to write its chemical formula. Okay, so we learned about the prefixes. So di and penta are our prefixes here. Di means 2, penta means 5. Then we just need to know what the actual elements are. Phosphorus and oxide, which is oxygen. So I'm gonna go, phosphorus is P, and it's diphosphorus, so it's gonna be a 2. And then oxide is oxygen, and it's penta, so it'll be 5. And these will be subscripts, so let me just fix that. Oops. Sorry. Okay. All right, let's go to letter B. I don't know what is going on here. Okay. B is pH4. So now what I need to know is that this is covalent. It depends if something is covalent or ionic in naming it, but because this is covalent, I will use prefixes. So let's see, we have phosphorus. Ooh, that's still in a subscript. We have phosphorus, and we have H4. So let's see. Oh goodness, I forgot what 4 is. Let me look back. What module? I changed some of the answers, or some of the questions, so I don't have the actual answer to this because I made it up and I don't know the answer. Okay, prefixes. Okay, 4 is tetra. All right, and that's on page 67 if you want to have the table for your exam. So again, page 67 has your ide atom names of nonmetals like oxide or nitride, all that kind of stuff. And it also has your table with your prefixes. So page 67 is going to be a great resource for you. Okay, so that means it's going to be tetrahydride. Okay. Letter C, and I want this together like I had it. Letter C, nitrogen trioxide. And they are giving me the name, so I'm going to do the formula. Nitrogen trioxide means there's 3. Tri means 3. Oxide is oxygen. Okay. Stop. All right. Sorry, I don't want so much space in here. Oh my goodness. All right. I know I'm probably killing you guys. Okay. Letter D, sorry. CAS. All right. This is going to be not in a subscript. We're going to write its name. And I know this is irritating. Okay. I know C is calcium. And I know S is sulfur. So if I look at the table on page 67, it's going to tell me that the ide name for sulfur is sulfide. All right, that's all your answers for number 4. Now let's look at number 5. Give the number of protons, electrons, and neutrons for the following atoms. Okay, letter A, I have a K, and it has the number 40 here. Now, if you remember, we have to look back at atomic number, which means I'm looking back at my periodic table again, and it looks like potassium, letter K, is number 19. So if it's number 19, that means that it has 19 protons and 19 electrons. So I'm going to go ahead and put that. Now I just need neutrons. So neutrons we get by subtracting the number that I'm given, and we subtract the protons. So let's see. 40 minus 19 is going to be 21. 21 neutrons, because your number here is your protons and neutrons added together. Okay, let's look at B. We have 132, and that's an I. So iodine is number 53, which means it has 53 protons, 53 electrons, because that's what the number on the periodic table is going to tell me. And let's see. We're going to subtract 132 minus 53. Let me get my calculator because it's too early to do that in my head. I don't really want to. Okay, 132 minus 53. That means I have 79 neutrons. All right, that's your answer for number 5. Let's move on to number 6. We're going to give the abbreviated electron configurations for these atoms. I kind of like this part, it's fun. All right, so what we're going to do is we are going to look at the periodic table, and this does say abbreviated, not the full electron configuration. So we're going to look at the periodic table. I'm going to find bromine, letter A, and that's going to be number 35. Once I find that, I'm going to look back to the closest element in the 8th column there that comes before this element. So that would be argon, number 18, because that is the closest one that comes before bromine. So it's going to be AR. Okay, let's see what number I'm looking at just to make sure I'm doing it right. What number am I on? 17, I thought. Okay. All right, so AR is going in brackets because this is abbreviated, so they want you to know this is the closest one. All right, AR is going in brackets, and then I'm just going to follow along on the table, and I'll kind of show you here if you can see. I don't know if it's backwards. So here's AR, and I want to get all the way to bromine. So I'm going to go from here to the next line, which is going to be 1, 2, 3, 4. This is 4s, 2. And then we're going to go here, which is 3D, if you remember, 3D, 10. There's 10 of those. And then we're going to go, this is P, level P, and we're going to go 5. 1, 2, 3, 4, 5, because there's bromine. So that is 4P5, I do believe. Okay, make sure I did that right. Yep. Okay, and these are going to be in superscripts. That is how many valence electrons they have in that level. You will put it in a superscript. Your number for the level is just going to stay as a coefficient. Okay, Let's do letter B. All right, letter B, MO. So I'm going to find that, and that is number 42 on the table. So again, I'm looking for the closest element in the eighth column that comes before MO. So the closest one I have is going to be KR, that's number 36. That's going in brackets. And then I'm just going to start counting down the table. So here I have KR. I want to get to MO. So I'm going to start here. This is 5S2. And then I'm in level 4D, and there's 1, 2, 3, 4 to get there. So 4D4. And then we got to make these, whoops. I didn't mean to do that. Sorry, I don't know what the problem is today. Okay, we're going to make these superscripts. So if you're writing it on your paper, this is what it will look like. Okay, that's your answer for number 6. All right, number 7, what is the Lewis structure? I'm not going to be able to do this one for you. Where is this? 22. I can show you the answer, however, in the answer key, so I'll do that. So the Lewis structure for H2CO. So first what I need to do is figure out how many valence electrons each of my elements have. So I have 2 hydrogens, and they each have 1 electron, valence electron. So that's going to be 1 per each hydrogen. Then I have a carbon. My carbon has 4 valence electrons because it's in the 4th column of the periodic table. So that's going to have 4. And then oxygen is in the 6th column, so it has 6 valence electrons. So I have 1 plus 1, that's 2, plus 4 for carbon, that's 6, plus 6 more for oxygen. So I have 12 to work with total. So I have to make sure when I do my configuration that I have 12 total valence electrons. Okay, so let's just start putting them in there. So because, let's see, carbon is going to go in the middle. And actually, you know what? I'm going to just draw it here. All right, so carbon is going to go in the middle. I'm going to have a hydrogen. Oops, why did I do that? I'm going to have a hydrogen over here. I'm having technical difficulties today, I'm sorry. Okay, I'm going to have a hydrogen here. I'm going to have an oxygen here. Okay, so let's start thinking about where everything else is going to go. Well, this hydrogen has all it needs because it has 2 valence electrons. This hydrogen as well. And carbon only has 6 right now. It needs 2 more. Oxygen needs 6 more. We have 12 to work with. So far we have 2, 4, 6. Let's start filling them in. 8, 10. Uh-oh, I only have 2 more to work with, and carbon and oxygen both need 2 more. So this is what I'm going to do. Double bond here. So 2, 4, 6, 8, 10, 12. And this is what your final Lewis structure is going to look like. Okay. Moving on, I'm going to go back to the exam. Okay. Number 8 says a chemist measures the mass of a chunk of wood to be 45.4 grams. When the wood is burned, 22 grams of carbon dioxide, 12.2 grams of ash, and 15.8 grams of water vapor are produced. How many grams of oxygen were used in the burning process? Okay, so what I need to do is see what I started with, which was 45.4, see what I ended with, which was all these numbers, right? And I know that I started with wood and oxygen. So I need the mass of all of my products, my carbon dioxide, my ash, and my water to equal the mass of the wood and the oxygen that was used. So what I'm going to do is add up all my products first. So 22 plus 12.2 plus 15.8, that's going to equal 50. So then I'm going to do 50 minus 45.4 because that was the mass of the wood, and this will give me what I had left, which would be the mass of the oxygen. I get 4.6, so the answer is C. All right, number 9, determine the shape of an SiCl4 molecule, give its bond angle, and draw a picture of it. Okay, let's see here. Let's go to where that is so I can make sure I tell you correctly. All right, so first of all, we need to first draw the Lewis structure. So I'm gonna go back to my whiteboard. Okay, let me clear this out. All right, so first of all, we're gonna draw the Lewis structure. So the question was for SiCl4. So let me go back here. Where did my board go? Okay, and Si is gonna go in the middle, and my Cl's are gonna go on the outside. I also need to count up how many electrons I have. I know chlorine has 7 a piece, so that's gonna be 28 for all my 4 chlorines. I'm not sure how many Si has. Let me look. Silicon. It has 4, so I have 28 plus 4. I have 32 valence electrons to work with. Okay, so far I have 1, 2, 3, I have 8. 2, 4, 6, 8, sorry. I'm gonna start filling in. 10, 12, 14, whoops, this is annoying. 16, 18, 20, 22, 24, 26, 28, 30, 32. This is an easy one. So single bonds here in the middle, and then all my other valence electrons are just filled in. They all have 8. We are good to go there. All right, so now that I see the central atom has 4 groups of shared electrons around it, I can determine that this shape is going to be a tetrahedron. All right, so it's going to be a tetrahedron, and as a result, because there's no non-bonded valence electrons around my central atom, I know that the bond angle is going to be 109 degrees. So let's go back to your test. Sorry, I'm struggling with flipping all these things today. Oh my goodness. I can't find Zoom now. Okay, there we go. Let's pull back up the final. All right. Bear with me. This is a struggle today. Okay. All right, now I'm back in the final. Okay. So this is going to be tetrahedron because it has all 4 pairs of valence electrons bonded with a bond angle of 109 degrees. Did I do that right? No, I didn't. I can't remember how you do a degree symbol. That wasn't it. I'm just going to put 109. Okay. All right, so that's your answer for number 9. The next question says, if a liquid goes through a phase change and all you know is that the molecules slowed down and moved closer together, what phase did the liquid turn into? This is a really easy one. You know that solids have their molecules the closest together and move the slowest. Liquids, they're a little bit farther apart, they move a little more quickly, and gases, the molecules are moving very quickly and are very far apart. So if it went from a liquid and its molecules slowed down and got closer together, we know that would be a solid. So that is an easy one. All right, next one says, to balance the following equation, what will be the coefficient in, I meant to put in front, not in from, I'm sorry, in front of the carbon dioxide. So first I need to know which one carbon dioxide is. CO2 is carbon dioxide, carbon, oxygen with a subscript of 2, dioxide, carbon dioxide. All right, so we need to balance it. So let's see. You could do your little table that we did before where you go, let's see. That's going to be hard to do right there. So let me do it. Let me do it here. Where you go reactants, products, and you do your little table. And we're doing, let's see, what are we doing here? We're doing carbon, oxygen, and hydrogen. So carbon, oxygen, and hydrogen, carbon, oxygen, and hydrogen. Okay, and we have 1 carbon over here. We have 3 oxygens because I have 2 here and 1 here, and 2 hydrogens. So 1, 3, and 2. 1, 3, and 2. And then I'm going to look on my product side. I have 6 carbons on the product side. How many oxygens do I have? I have 6 plus 2, so I have 8. And how many hydrogens do I have? I have 12. All right, let's see what's going to be the easiest thing to do. I think that we should go ahead and put a 6 in front of this CO2. And that will give me 6 carbons. So it's going to give me 6 carbons, but it's also going to change my oxygen number. So I have 12 plus 1, excuse me, I have 13. Okay, let's see about hydrogen here because this one's going to be a little complicated since I have an odd number. All right, so let's see about hydrogen. How about we put a 6 in front of this hydrogen to make that 12? So now that's 12. And now I have 6 oxygen here and 12 here. So I have 18 oxygen. Okay. And let's see. That means the only one we have left to change is oxygen, and we need 18 on this side. So the easiest thing for me to do is going to be to put a 9, and no, not a 9. We have 6 here. So 18 minus 6 is 12, so that means I need a 6 here because I need 12 more. So now I have 6 plus 12, I have 18. And everything else adds up. I have 6 carbon, 6 carbon. I have 12 plus 6, so I have 18 oxygen and 12 hydrogen. All right, so number in front of my carbon dioxide is 6. So actually the answer is going to be none of the above, surprisingly. All right, moving on. Number 13, classify the following reaction. 2H3PO4 produces 3H2 plus 2P plus 4O2. Okay, well, we started with one substance, one compound, and it produced all these elements. So if we start with one and then we're breaking it down, that is called decomposition. Letter A. All right, number 13. Okay, trying to follow along with the answer key and make sure we've got everything. All right, number 13, how many moles of K2CO3 are in 151 grams sample of the compound? Okay, so we have to go from grams to moles. So I'm gonna do it over here. So 151 grams. 151 grams of K2CO3. And I'm going to put that over 1. That's my given value. I'm going to multiply it by a conversion factor. They're asking me for moles. So it's going to be how many grams are in 1 mole. So 1 mole is going on top, and I need to find out how many grams of this are in 1 mole. So I'm going to look at the periodic table and start adding. So K, potassium, has 39.1, and that's going to be times 2, right? Because there's 2 of them. Okay, so that's 39.1 times 2. Added to carbon is, let's see, 12. And that's going to be added to oxygen, I believe is 16. Yep, 16. And I'm going to put it in parentheses because we're multiplying 16 by 3 because I have 3 oxygens. Okay, so that's how I add up my molecular mass. So 39.1 times 2 in parentheses plus 12 plus parentheses 16 times 3. 138.2. Whoops. 138.2 grams. I'm going to put it in the calculator. We're multiplying through, so I have 151 times 1 divided by 1 times 138.2. So really I just have this number divided by this number. The ones are going to cancel. And I'm sorry, I didn't mean to mark out moles. The ones are going to cancel and the grams are going to cancel, and then we'll be left with moles. Okay, so 151 divided by 138.2. I got a long number, but basically it rounds to, we need how many significant figures? 4 significant figures. So I got 1.093 moles. Okay. And that is going to be letter B. All right. Number 14, what is the limiting reactant when 2 moles of KCl are reacted with 3 moles of magnesium dibromide in the following reaction? 2 KCl plus MgBr2 produces MgCl2 plus 2 KBr. Okay, so we're trying to figure out what the limiting reactant is if we use 2 moles of KCl and 3 moles of MgBr2. Well, the definition of a limiting reactant is going to be whichever reactant runs out first. So if I'm using 2 moles here and I'm using 3 moles here, it looks like in the chemical reaction, for every 2 moles of KCl used, I'm only going to use 1 mole of MgBr2. So once I use those 2 moles of the KCl that they gave me, it's going to be ran out, and I'm going to have 2 moles left over of MgBr2 because I only used 1 mole. So that means the KCl will run out first, which means it is the limiting reactant. Okay. Number 15, and let's see where I'm at. Okay. Let's see, number 15, which of the following are empirical formulas? Well, as you remember, hopefully, empirical formulas cannot be simplified anymore. So here we have C18, H36, and O18. Well, these can be simplified a lot because 18 goes into 18 one time and 18 goes into 36 2 times. So we could make this go down even smaller to CH2O. So this is not empirical. This one we have Na2, S2, and O3. Well, 2 and 3 don't have any common factors. Did I say that right? Sorry, I'm not doing math right now. But nothing can go into these numbers other than 1. So that means this is an empirical formula because it's as simplified as I can get it. All right, let's see how many we have left. We have 27, and I'm on number 16. Okay. Number 16, to make a phosphorus fertilizer, agricultural companies use the following reaction. If 151.0 grams of Ca3P2O8 are reacted with excess H2SO4 and H2O, how many grams of fertilizer can be made? Okay, I'm given grams of one substance. I'm asked for grams of another substance. So this means our favorite thing, stoichiometry. All right, so first I'm going to convert 151 grams to, let's see, and that tells me it's the limiting reactant, so I know I can use this value. I'm going to convert this. If I want to use stoichiometry, I always have to convert to moles. So I'm going to convert these grams to moles, and then I'm going to go from moles to grams of the fertilizer. Okay, or moles to moles and then moles to grams. Sorry, 3 steps. Okay, so first of all, I'm going to clear this out. I'm going to have 151, and that was grams of Ca3. Whew, maybe I should type this. 151 grams of Ca3P2O8. And that's going to be over 1 because it is my given value. And I'm multiplying it by a conversion factor. My conversion factor is going to be, I'm going to moles, because like I said, you have to have moles if you want to use stoichiometry. So 1 mole, and I need to find out how many grams are in 1 mole of this substance. And we're going to do it just like we did in the previous question. So look at the periodic table and find the mass for calcium, multiply it by 3. Mass of phosphorus, multiply it by 2. Mass of oxygen, multiply it by 8. Add them all up. When you do that, you're going to get 310.3 grams of Ca3P2O8. Okay, that is going to give you, so you would do 151 divided by 310.3. That's going to give you, I'm going to round, 0.4866. And that's moles of Ca3P2O8. Okay. Now I'm going to take these moles to go to moles of my other substance. So I'm going to have 0.48, oh, why am I not typing? 0.4866 moles of Ca3P2O8 over 1, because that's my starting value. Multiplying by another conversion factor. Let's look back at our equation to see what conversion factor we're going to use. So we're going from moles of this to moles of fertilizer. So I need to look at my coefficients in the equation. So for Ca3P2O8, I have a coefficient of 1. And for fertilizer, I have a coefficient of 1. Okay, so you could skip this step if you wanted to, because it's just going to be 1 mole over 1 mole. Pretty easy, which means you're just going to get the same answer. Okay, excuse my handwriting. All right. So I'm going to get 0.4866 moles of fertilizer. Okay, now I need to go this number to grams because they asked me for grams of fertilizer. So my starting value again, 0.4866 moles of fertilizer over 1. And my conversion factor is going to be, I want grams, so that's going to be in the top. Moles is going to be on the bottom. And we know that we're going to find out how many grams are in 1 mole. So it's going to be 1 mole on the bottom. Now I'm going to look at the periodic table. And for fertilizer, we're going to look at the mass of Ca plus the mass of hydrogen times 4 plus the mass of phosphorus times 2 plus the mass of oxygen times 8. So that would give me 234.1 grams. And when you put that in your calculator, 0.4866 times 234.1, you're going to get 113.6 0.913. Let's see, I need to round. Let's see how much I need. I need 4 significant figures. So we need to take away some of these. So 113.9, and that's grams of fertilizer. Okay. That was a 9-point question. All right, we are over halfway done. I'm going to call it a day, and we will finish the review of our practice test tomorrow. Again, I only received 1 practice test, so hopefully you guys will go back and watch this so that you can have something to study for your final exam on Wednesday. If you have any questions, feel free to reach out, and I will see you guys tomorrow.